Hello and welcome to the second series of talks as part of the Tufts Graduate School of Arts and Sciences Graduate Student Speaker Series, or the GS4. Today is my pleasure to introduce Nate Fisher from the Department of Mathematics. Nate will give his presentation and will allow a few minutes at the end for questions. Nate, I'll turn it over to you.
Well, thank you for having me, and thank you to the Graduate School for organizing this summer series. I think it's a really cool opportunity. And it was a unique challenge to take this math research that I've been working on for a couple years and try to boil it down to the main ideas to talk about it to a non-math audience. Yeah, I'm excited to show you what I've come up with. And so today we're going to be talking about random walks. I'll explain what they are. And we're going to be taking these random walks in a space called the Heisenberg Group. And we want to know what happens if we keep on walking as we move on to infinity. I just want to take a quick moment to say that tomorrow, June 10th, there's a strike for Black Lives. And so it's calling attention to the marginalization of Black people in STEM and in academia. So I know that personally I moved my office hours, so I don't have office hours tomorrow. And I'll be taking a break from research to do some reading and try to stay informed. So consider taking part in that if you have the chance. Okay, so first we should start off with what is a random walk? And so let's imagine that an alien robot lands in the middle of a desert and its goal is to search for human life. How is it going to do this? Well, it's being programmed in a certain way. First, it will randomly pick a direction. It'll either choose north, east, south, or west, and then it'll take one step in that direction. So here on the right, we have a little spinner. It randomly chooses east, and so our robot takes one step east. Then it repeats the process. After each step, it'll choose a new direction at random and then take one step in that direction. And so here, the second step was randomly chosen to be in the north direction, and so it takes one step north. Now it'll continue this process. So a question we can ask is, where might the robot end up after 100, 1,000,000, or infinitely many steps? What is the long-term behavior of such a random walk? So if we assumed that this desert were actually an infinite flat plane and not on Earth, which is actually round, what would happen? Well, in 100% of the sample path being a possible infinite random walk, so an infinite number of choices of directions and steps that you took. Well, in 100% of them, the robot would wander out, but then come back to where it started infinitely often. And so I kind of sketched it out here. So let's imagine it starts going up, it goes over, and then it winds its way back to where it started, and then it'll venture out again, and maybe it'll go a little bit farther this time, but eventually it'll come back to where it started. And so no matter how far out it goes, it's always going to end up coming back to where it started. And a quick side note, so 100%. In math, that does not mean that every single possible sample path will do this, will have this behavior of recurring back to where it started. Because it's perfectly possible that at every step it chose north. And so it takes one step north, and then again it chooses another step north, and then it'll just keep going up and up and up forever, and it won't come back. But that's just one situation, and it has probability 0. And so when we're talking about 100%, we just mean a really, really large proportion. It's not all of them, but 100% of them. Cool. And so the Heisenberg Group, which is where we want to take our random walk, is a 3-dimensional space. But still, we're only going to let our robot choose randomly between 4 directions: north, east, south, or west. And you might say, wait, it's 3-dimensional, what about up and down? In the Heisenberg group, we don't need to give the robot those up and down choices. Why? Because when the robot takes one step east, then north, then west, and then south, in a plane, it would end up back where it started. In the Heisenberg group, it actually ends up floating in the air. It's above where it started. So by moving in this square, it actually moved up 1 unit. And so that's something that we'll explore a little bit when we define the Heisenberg group. But yeah, so in the Heisenberg group, things will be a little bit more interesting, a little bit more complicated than it is in the plane. So in mathematics, this journey that a robot takes is called a random walk, which I think is a good name for it because it's just a sequence of random steps. And it's an example of a random process. And random processes come up a lot in mathematics, and also they have a ton of applications in a lot of different places. So my advisor, Moon Duchin, works on gerrymandering and redistricting maps. And one of the tools that Moon and her team use are Markov chains, and they use Markov chains to randomly generate district maps in a way that hopefully creates a non-gerrymandered map. I was looking at Wikipedia yesterday, and I don't know if anyone else played this game, Hi Ho Cherry-O, but I played it. I remember playing it as a kid, and I read that it's the game is can be described by a random process, by a Markov chain, which I thought was interesting. Predicting stock exchange, and then particle motion and Brownian motion are examples of random processes that you can use mathematics to study. And so what is the Heisenberg? What Heisenberg group? What is this three-dimensional space? Well, it has a bunch of applications in optics and mechanics, but what really interests me is the beauty of the geometry. Oftentimes people, when I say that I'm studying math and they ask me what I study, they ask like, oh, and what is it used for? Well, what I do doesn't have like concrete applications that I'm aware of, but that's okay. Because math can be pretty and beautiful in of itself, and you don't necessarily need an application to study it. So that's why we're talking about alien robots taking random walks. But this Heisenberg group is a three-dimensional space where we measure distances in a different way than we're used to in our normal three-dimensional space. And so what does that mean? Well, it means it's a three-dimensional metric space, but the metric, the distance function, is different. And so what is a metric space? It's just a collection of points, it's a space, and we assign to it a distance function that measures the distance between 2 points. And it must satisfy 3 properties. The first one says that the distance between 2 points is either positive or 0, and it's only 0 when you're measuring the distance between a point and itself. The distance between x and y should be equal to the distance between y and x. The order in which we choose our points shouldn't matter. And this last thing is the triangle inequality, and it's just saying that triangles look like the way we want them to. And so what are examples of metric spaces? So this R represents all real numbers. And so the set of all real numbers is the number line. And we can measure distance by taking the absolute value of the difference between those 2 values. Another perfectly good metric space is the plane. And you might remember from like middle school math that this is the distance formula for 2 points in the plane. And over here, I've drawn the circle, which is the set of all points, which are distance 1 from the origin. And one more example of a metric space. So we could take this same 2-dimensional plane, but now we're going to define the metric in a different way. Instead of using the standard Euclidean distance formula that we learned in school, we're going to say that the distance is equal to the difference in x coordinates here plus the difference in y coordinates. And you can work it out that this diamond we see here is the circle. It's the metric circle for this metric. It's all the points which are distance 1 from the origin. And this metric is called the taxicab metric. And why? Well, it's kind of related to, like, you can think about it as a grid, or think about it as if you were in a city like Manhattan. If you're starting at point A and you need to get to point B, you cannot go through buildings. You have to go along streets. And so this red path is an example of a path between point A and point B, which is the shortest path possible. And I'm pretty sure it moves like 12 blocks. It'll go up 6 streets and then over 6 avenues. And so notice that this, like, the distance here is actually measuring how far we're moving in streets and how far we're moving in avenues. And so you can see where this formula comes from. We're measuring the distance in x and the distance in y and adding those two together. And these red, green, or red, blue, and yellow lines are all examples of geodesics, which are the paths which realize the shortest distance between 2 points. And so we could look at this red, this blue, and this yellow line. All of them are like 12 units long. They move 12 blocks. And this green line is not possible. We're not allowed to go through buildings. And so that is not a geodesic in this metric space. It's not a path that actually no, it is a geodesic, but we're not going to allow it because we want to think about moving through blocks. Cool. And so those are some examples of metric spaces, and the Heisenberg group is another metric space. It's a 3-dimensional space where we assign a different metric, a different distance function. And this metric or this distance formula is not easy to write down, but it is related to the taxicab metric on the plane. And so if I'm not going to write down the formula, how can we hope to understand it? Well, we can consider what geodesics, what do length minimizing paths look like? And also, what does the sphere look like, the metric sphere? If we look at all the points that are distance 1 from the origin, what does that set look like? In our normal 3-dimensional world, it would just be a sphere. And now I'm going to call it a metric sphere because it's not going to be round here, but it's still the set of all points which are distance 1 from the origin. And so first we can look at geodesics. Geodesics in this Heisenberg group have square-like shapes. And so this blue line is an example of a geodesic. Notice that its shadow, if we project this path down to the XY plane, it looks like a square and it traces the perimeter of a square. That'll be important. And the height of the path is equal to the area enclosed by the shadow so far. And so notice at this red point, we could project it down, and then we have this red area. If we calculated that area, that would be the same as the height of the path at this point. And then if we kept going, we would we would enclose the area of the full square. And so up here, this height will be equal to the area of the full square that's not fully shaded in this picture. And so notice that this looks kind of like what happened to our robot before. Our robot took a step east, then north, then west, and then south, and then it ended up higher than it was before. And that's because it was tracing one of these geodesic paths. And what does the sphere look like? So again, the metric sphere is the set of all points which are distance 1 from the origin. And it looks like this. Definitely not round. And so I said before that the this metric is related to the taxicab metric. And remember that taxicab metric had the unit circle, or had a metric circle that looked like a diamond. And so if we look at the sphere from above, we see this diamond-like shape, and that is not a coincidence. And notice that like here we have like some some angles, some sharp angles. It's definitely not a round sphere. And in these pictures, I did not draw the vertical walls so that we could see through it. So to complete this picture, we would draw vertical walls filling in these gaps. And so that's what our spheres look like. And notice that they're like kind of little divots, little dimples coming in on the north and south poles of our sphere, which makes for a strange geometry, but I think it's really pretty and interesting. So now let's get back to how we started, and let's think about this random walk. So if the robot takes infinitely many steps in random directions in the Heisenberg group, what happens? Well, the geometry of the Heisenberg group is a little bit more complicated than that flat desert, and so the problem is more interesting. Unlike before, the robot in general will not keep on returning to where it started. It will walk off to infinity in the Heisenberg group in a lot of sample paths. And so what does it mean to walk off to infinity? Now we want to talk about boundaries of metric spaces. One example of a boundary is the visual boundary. So let's imagine we're back in our normal three-dimensional world, and we want to think about how many different ways could we like look off to infinity. Well, how many different directions could we look in a three-dimensional space? Well, there's a sphere's worth of directions in three-dimensional space. And so the visual boundary, i.e. which parameterizes the directions in which you could look, would be a sphere. But this boundary depends on geodesics, and I'm not going to get too much into the technical details, but geodesics in the Heisenberg group are weird, and also they're not unique. And so like this visual boundary of like following geodesics and looking off in different directions doesn't end up working well for our metric space, even though it is a nice intuitive thing to think about. And so instead we're going to think about the Hora function boundary, which isn't quite as intuitive, but it plays nice with the Heisenberg group and also with other strange metric spaces. And generally, this boundary in a way is dual to the metric circle or the metric sphere if we're in 3 dimensions. And what do I mean by dual? By dual, like I'm kind of going to restrict to the 2-dimensional case now to describe what dual means, and think about polygons. And so dualizing is a process which turns edges into vertices and turns vertices into edges. And what do I mean by that? And so here, this is the circle, the metric circle that we got from the taxicab metric. Let's imagine that these are these are just other shapes, a polygon and a circle, an octagon and a circle. What is the dual of this diamond? Well, for each edge, we'll get a vertex, and each vertex will get an edge. We get something that looks like a square. And if we were to dualize this square, we would end up back where we started with a diamond. In this octagon, there are 8 edges and 8 vertices, and so its dual should also have 8 edges and 8 vertices. So it's going to be another octagon, but it's going to be shaped differently. And you might say like, hey, like this square and this diamond are kind of just like rotations of each other. And like, maybe the same is true about this octagon. And like, yeah, maybe they are rotations of each other. That's possible. But in metric geometry, we care that the rotation has happened. That makes them different shapes in our world. And finally, this circle, you can kind of think about it as a polygon with infinitely many edges. And so if all of the edges are going to vertices and vertices to edges, we're going to get something else that has infinitely many edges. So the dual is, we get the circle back. And so let's look at a couple examples of Hora function boundaries. So R2, let's look at the plane with the standard Euclidean metric that we're used to. Here we have the metric circle, which actually is a circle. And I said that the boundary should be dual to that. Well, the dual to a circle is a circle, and indeed the boundary is a circle. And another example, if we look at the plane again, but with the taxicab metric, the metric circle was a diamond, and we should get something dual to that in the boundary, and the boundary is a square. And so what is the Hora function boundary of the Heisenberg group? This is what I've been working on for the past year or so. And so we already looked at our metric sphere, and it was kind of diamond-like, and now I've drawn it with these vertical walls showing, and I've color-coded it. So the boundary maybe should have some square-like shape, because the square is dual to the diamond, and in fact it does. So this purple region here is a square, but then we get a lot more stuff going on because this is a really weird metric sphere, and when we do this process of trying to go out to infinity, we actually get something kind of wonky. But in general, it has this it preserves this dual square shape, and the colors kind of correspond to, if you went to infinity in the direction of orange, you end up at this orange circle, for example, or if you went to infinity at the orange in the direction, like in the northern direction, like this purple direction, you actually end up in this purple square. Cool. And so why were we looking at this boundary? Well, we were using that boundary to try to say where our robot is most likely to end up after infinitely many steps in its random walk. And so this is still a work in progress, trying to see where a random walk will end up in the boundary. But what can we say if we approach the problem from a different direction? We're going to take our metric sphere, we're going to dilate it, we're going to stretch it out so that it has a really large radius. Then we ask the computer to simulate a random walk until it runs into this dilated sphere. Record where it hit the sphere, and then repeat the process for many, many times to try to get an idea of which directions these random walks are going in. And so we have some experimental results for this. So we've dilated this sphere to radius 100, which really isn't that big, but the computer can't handle much more than that. At least my computer can't. And then we simulated 5,000 sample paths, 5,000 different random walks. And we let it run until it hit the sphere of radius 100. And what did we see? And so here in this picture, we have all of the points where it hit the sphere of radius 100. And then down here, we kind of keep track of the X and Y coordinates using the symmetry of the sphere to put everything in one quadrant. But really, what do we see? We see that 50% of random walks hit the vertical walls of the metric sphere, and 50% of them hit either the ceiling, like the roof, or the basement of that metric sphere. And that's not what we expected. We expected it to always go in one direction or another, but this 50-50 split is strange, and we're not sure where it comes from. And just a side note, the average robot, the average random walk took about 4,200 steps before reaching the sphere, which is a lot, which explains why we kind of had to restrict this radius to 100 so that the computer could handle it. Because the average random walk is going to go out a little bit and then wander around before it shoots off in a direction and hits the sphere. So future goals are to understand this 50-50 split and then relate the experimental data to how random walks go to the boundary. How do they go to infinity? And so that's it, and thank you.
Thank you, Nathan. We have a couple more minutes. If anyone has any questions, you can unmute yourself and ask the question, or ask the question in the chat and I will read it to Nathan.
I can ask a question. So you seem surprised by this result. There's a 50-50 split, as you said.
Right.
So maybe very naively, but I would have expected, well, if you're just taking a random walk until you hit the boundary, you would get sort of a random distribution, sort of uniform.
Right.
So why would you expect it to all land in the same place?
Yeah, so yeah, maybe not all in the same place, but we kind of expected it to either like go more horizontally or go more vertically. We didn't expect it to split this way. And there are some numbers, like it's weird that you can kind of take the Heisenberg group and kind of split it into horizontal directions and vertical directions, and the ratio between those two is like 19 to 12. And so this 50-50 split is surprising. I think if we were to, like, I think my advisor was hoping for a 19 to 12 ratio instead of a 1-to-1 ratio.
I see.
Nate, do you think that this kind of approach could generalize to higher dimensional Heisenberg groups?
And not exactly like this. The metric spheres in higher Heisenberg groups are not understood very well. And so, in like the way that we study this stuff relies heavily on the geometry of that sphere. But it's one of our goals is to try to generalize this to Heisenberg group and then see what we can say about other like nilpotent groups or cardinal groups.
Cool.
All right, we were just about at time. Thank you, Nathan.
Thank you.
Again, this session is being recorded and we will share it. If you have any questions, I'm sure that you can email Nathan. And again, we thank you for joining us today.